Hi everyone. As Matthias gratefully presented me, my name is Manuel Yin. I'm coming from the Royal Institute of Technology in Stockholm, Sweden, and I'm presenting work today titled EdgeDroid, an experimental approach to benchmarking human-in-the-loop applications, which was developed along with my co-authors Junji Wang, Satya, and my advisor who could not be here, James Gross. So, to start with, we all know this exciting new category of applications that is currently proliferating, these AR, wearable cognitive assistance applications. That basically all what they do is put the human in a feedback loop with the system, where the human provides, how do you say, high-dimensional context-aware inputs, and the system replies with human parsable output, so natural language or images or instructions. And these applications are really interesting for a lot of fields. So they can improve training, the entertainment, and so on and so on. And thus they're starting to proliferate. But we have a problem. There's currently no way to accurately benchmark or study these applications. We need to know how they interact with each other for massive deployments. We need to understand how they interact with infrastructure. We need to understand how they scale. And as I said, so far we identified that there's not really a methodology for this yet. The way it's done is that basically everyone who's trying out these new applications, everyone that's deploying them, is just taking users and trying out the application and measuring what's happening on the system, what's happening on the back end, or what's happening on the network link. But this works for one user. It might work for 10 users. But what happens when you have 50 users, or you want to test out your application with 100 users? Well, that becomes costly, and it's not very repeatable because you're dealing with humans, and humans are, unpredictable. I also I put it together with costly, but it also takes time, and we all know time is money, and you cannot automate this. So before I go into what we propose to solve this, I want to talk about a bit of what has been done in this field of applications. We identified there's been a lot of work in prototyping. There's been a lot of creating these cool applications. The same group that I'm collaborating with created a platform for these wearable cognitive assistance applications. And other people have created new applications. There's been also some work on latencies, again, studying just on a per application, single application basis, but not a methodological approach to this. And finally, there's been some modeling work, but it doesn't really capture what needs to be captured. So what we propose here today that we present is a threefold contribution. We'll present first a methodology for benchmarking these applications. I might say it straight away, it's a trace-based methodology. We present an implementation of this methodology, a tool suite that we provide, that we call EdgeDroid, hence the name of the presentation. And we will present a set of experiments and measurements that show what we can obtain with this methodology. So moving on to the approach, as I said, benchmarking these applications is hard. Why is it hard? Because we have a human, and humans are not reliable, okay? So of course our first idea was then, okay, but what if we take away the human? What if we cross out the human and replace the human with something else? And here's the crux of the issue. Here's where our work comes in. So we propose a methodology-based, trace-based methodology in which we record what the human user does, and then we replay it to the system. We don't replay it straight as it was recorded, and I will get into that a bit later in my presentation. That's the user model that you see there. But if we could do this, then this would be repeatable, and it will be scalable, and it will be a lot more convenient than just having users trying out the applications. So in order to explain our methodology, I will run an example. I will use a task guidance wearable cognitive assistance application, which is this application which guides a user in the assembly of a Lego model. This application was published previously. We used it because it has a very linear model, and then it's very easy for us to use it for initial approach, since we can logically understand it as an application that has to pass through several stages in a linear fashion before it reaches a desirable state. And I will use this application to explain then how our system works. This application, by the way, it receives visual inputs in the form of a camera feed, and it replies to the user in the form of an instruction in sound form and voice spoken, and an animation. So what we do first is, the first step in our methodology is recording the trace. Here what we do is we record the raw input provided by the user to the application before it passes through any sampling that the application itself does. This way we capture basically what the user sees and what the user wants to provide to the application. In the case of Lego, again, this will be a stream of frames of what the user is doing. And this trace, of course, contains all the timestamps, at which point in time the user does this action, or at which point in time the user receives an instruction. But then we run into a problem. Just replaying this is non-trivial, because in my work, for when the system is in exactly the same conditions as when you recorded it, but what happens if you start scaling up and you start getting all these effects between applications? The backend might slow down, you may have more loss on the wireless link, and so on and so on. So these delays, these changes in system responsiveness, they affect the user as well. And thus, we cannot just play out the trace and expect to get a reasonable result. And that is where the second part of our approach comes in which we try to modulate, so to speak, or adapt the trace to the reigning system conditions. And this is, of course, very task dependent. Again, we're focusing on this linear task in order to be able to understand the task as a set of linear steps that we can traverse. And thus we can segment this trace into specific steps that we can then replay or adapt or roll back if we identify that there's an error in the system. So moving on quickly through implementation. I know this slide is a bit complicated, and you can, if you're interested in how we implemented this, you can look at our paper, or you can look at the implementation itself. But what is important to understand here is that we're only emulating a user, so we're not replacing the backend, or we're not replacing the network, because that's basically what we want to measure. So we basically remove the user and replace them with a simple Android device where we can run our fake client. And this can also run parallelly to the real application at the same time, because the idea is that it provides the same load that a real user would. So moving on to the evaluation. So before I move on to this section, I want to make clear that we're not here presenting. We do not want to evaluate the application we're showing. We want to show the results you could get. Again, we're still using Lego as a running example, which is a very simple application. But the idea was here to show, okay, these are the set of results, these are the set of scenarios that you can get with this application. Our setup uses, again, Lego. We set up 4 different scenarios, 3 scaling scenarios with a different number of devices to show that we can run these emulators in parallel and have them generate realistic load, and an additional scenario in which we impair the network link in order to get an external effect in the system and see that it shows up in our results. What we're mostly interested in here is delays, because that is what the user will experience, and that is what all the work has been focused on the delays in the system. So here you can see a set of results that we got. Don't focus too much on the numbers. The numbers are not what's important here. What's important here is that these are 3 sets of experiments that explore different angles that this approach can be used for. In the upper left, you can see a study on the differences in latencies between inputs that were, I put here state change versus no state change because I was thinking about this linear application. But in reality, you can think of it as inputs that were discarded by the application immediately or that were processed. And you can clearly see the difference because, of course, when an input is discarded, it doesn't pass through the rest of the recognition pipeline of this application. This could be, for instance, interesting for an app developer that's trying to understand how their application behaves in terms of delays when it's really deployed. On the right-hand side, you can see that segmentation of these delays across pipeline segments. So we can study, okay, so where are most of the delays for our application coming from? Are they coming from the network? If they're coming from the network, are they coming from the uplink or the downlink? Are they coming from the processing? Which could be interesting for instance, a system designer, someone who wants to deploy these applications and want to understand where the delays are. And finally, we can also zoom in, again, from the focus of an application developer to understand how the delays are distributed across the different task steps of these applications. If the trace is annotated, we can understand, okay, this was step number 6, so this is when the user needs to put the green brick on top of the blue brick. That has an average delay that is higher than the rest. Okay, why is that? Do we have a problem in the logic of our application, or is something that we need to fix? So, to start closing a bit, we understand that there's a lot of work here to be done. Although our system works and we're very proud of it, we believe that we can better represent the human. The human we have now is just simply a dumb robot that does this task that we told it to. But we really want to move a step forward and try to capture key components of human behavior, such as what happens if the delays start getting so long that the user starts getting irritated. How many more mistakes do they make? Can we model that? And that is something where we are exploring for our next stage. We also, of course, want to extend this benchmarking suite to other types of applications, not only linear task-based, but more interactive applications that do not have a set end state, so to speak. So to close here, just a summary of what I presented. I presented that there is a need to studying these applications. I think we can all agree on that. And this is difficult due to the human user. Again, the human is unpredictable, is not very good at repeating tasks and so on. And we presented a methodology and a tool suite for this task, which is trace-based and based on a model of human behavior, as we call it now. And we presented several results which show the utility of our approach. And thank you. I will take your questions now. Thanks.